So we're going to be looking at electrochemistry. This is chapter 20, and for the electrochemistry during this semester we're going to be looking at sections 20.1 to 20.3 in your textbook. We're going to break the lessons down into 3 sections. We're going to look at section 1, 2, and 3 individually. The first 2 sections that we're going to be looking at are sections 1 and 2, and we're going to be able to learn a few skills such as understanding terminology such as half reactions, oxidation, reduction, and of course reducing and oxidizing agents. We're going to be able to describe what's happening physically during these types of reactions, and we'll be able to write the half reactions, correctly assign oxidation and numbers, which you guys have already looked at, as well as balance oxidation and reduction reactions in acidic and basic conditions. We're going to go ahead and do a quick review of determining oxidation numbers. We've already looked at this in class a few days ago, but we'll go back over it again for the sake of this unit. Free elements, or elements that are in the uncombined state, have an oxidation number of 0. So what do we mean by that? Well, sodium, beryllium, potassium, all these examples here that we see, these are all examples of just elements on their own. So when we write these in chemical reactions, a lot of times it'll be like Na, subscript S, because they're solid. Sodium occurs in a solid state, plus whatever else. But also you notice that we have a couple of the diatomics, which we would write as, for instance, H2 gas, right? Something like that. But these are elements that are occurring naturally in their natural state. These will have an oxidation number of 0. Monatomic ions, or ions with just a single type of atom present, those are, or a single atom present, excuse me, those are going to have the charge that's assigned to them. So a lithium ion, we know it's +1, so the oxidation number is 1. This iron 3+, the oxidation number on the iron has to be 3+, and the same thing goes with anions. The oxidation number of oxygen, as we saw in Rule 2, is typically -2. So the default should be -2. If you're in doubt, that's where I would start. Now, there are exceptions. If we look at H2O2, or hydrogen peroxide, the anion that we have is the peroxide anion. And what you should notice there is that we have 2 oxygens that are each being, or 2 oxygens that are bonded to each other with a 2- charge overall. So what happens here is that the 2 oxygens, that 2- gets spread over the 2, so each oxygen has a -1 charge. So this is an exception rather than the rule, although it is quite common. Oxidation number of hydrogen is normally +1. We know that hydrogen is in group 1, so it usually follows those trends. However, there is a big exception. Okay, big exception, and that's when it's bonded to metals. Okay, and so let's look at this. Lithium aluminum hydride. Yeah, this is a very common reducing agent used in organic chemistry. The hydrogens here, okay, these are called hydrides, and they actually have a -1 oxidation state. Notice it's bonded to a metal, and in this case, this is one of the few cases where you will see hydrogen have a -1 as opposed to a +1 oxidation state. Group 1A metals, as well as group 2A metals, those are always either +1 or +2. So basically they match their position on the main group of the periodic table. And then fluorine, our greedy friend fluorine, is always -1. Remember, it's the most electronegative element on the table, so it subsequently desperately wants to have that -1 charge. Now, the sum of the oxidation numbers on all compounds or molecules are going to have to equal the sum of all the oxidation numbers. So, example, quick one, right? Sodium, we know that it's going to have a +1 charge. Chlorine, or this chloride, excuse me, ion, is going to have a -1. So, +1 -1 is going to equal 0. That was the original charge. There was no charge on sodium chloride, so it makes sense that the sum of our 2 oxidation numbers is going to equal 0. As another exception to the rule for oxygen, we do occasionally see this superoxide ion. Okay, and if you look at it here, notice that there are 2 oxygen atoms. Now, on those two oxygen atoms, you have a -1 charge. So what ends up happening is that each oxygen is going to have a -1/2 charge. These integers are, these non-integers are pretty rare. They don't occur very often, but when they do, just don't be too surprised. Be aware that they are actually capable of existing. So let's go ahead and let's just do a little quick practice problem. We have an ion down here, and let's go ahead and let's assign all the oxidation numbers. So listen to the thought process as I go through each of these. So what I'm going to be doing is I'm going to, first of all, look at the ions that I'm confident in their oxidation number. Okay, so hydrogen for sure here, we look at our hydrogen. It is not attached to a metal, so we can be very confident in the +1 oxidation state. And with oxygen over here, okay, we know that oxygen is typically -2. So we can be very confident in our -2 oxidation number. Now remember that our oxidation numbers for each of the atoms that are part of the molecule or ion must sum to the overall charge of the ion. And in this case, we have a -1. So what we're going to do is we're going to take our numbers, our oxidation numbers that we know, and basically solve for the missing variable. Okay, so we know that we have oxygen 2-, and we know that we have 3 oxygen atoms. So down here we have 3 times -2, okay, and that's going to give us, obviously, -6. Okay, we're then going to take our number of hydrogen atoms. Okay, so we have only 1 hydrogen atom. That's what our subscript tells us. So 1 times +1 gives us 1. So +1. Okay, plus carbon, because we don't know what it is, and that's going to equal our -1. Now, -6 plus 1 gives us -5, plus C is going to give us -1. Okay, so what does carbon need to be in order to give us an overall -1 charge? Well, it needs to be +4, right? Because -5 plus +4 is going to give us an overall -1 charge. So let's continue to look at a few more examples. So this IF7. Okay, so remember one of the rules was that fluorine is always a -1 charged ion. Okay, and we know we have 7 of those. So we have each one of these oxidation numbers being -1, and we have 7 of them. So 7 times -1 is going to give you -7. So in order to have a neutral molecule, which if you notice the IF7 doesn't have a charge, we need to have our I completely counterbalancing all the ion charges that are coming from the fluoride. So if I have -7 as the number, +7 is what my iodine is going to have to be. And you can look below here and you can see these examples down here. Each of them show different kinds of rules and different kinds of setups. Just a thing that I want to mention when you're assigning oxidation numbers, remember that you're not assigning the oxidation numbers based on the number of atoms present. So you're not going to write, for instance, a -7 here above the F6. What you're actually going to be writing above it when you start doing tracking later is you're actually going to write the oxidation state of just the single element. So -1 corresponds to the fluorine, okay, but +7 actually corresponds to the single iodine there. So this is how you'd write the oxidation numbers when you do your tracking later on in the unit. So let's go ahead and let's take a look at oxidation states and reduction reactions. This is covering section 20.1. So what we need to understand is that oxidation and reduction, they occur simultaneously. Okay, so something needs to be being oxidized and something needs to be being reduced in order for these reactions to actually happen. So something has to give up electrons, something has to gain electrons. So when something is oxidized, we refer to it as being a loss of electrons. So something has lost electrons. So if my sodium ion loses an electron, it's going to become Na plus 1 electron. Okay, and this is kind of a look at the half reaction. Okay, same thing. If something's reduced, okay, it's gained electrons, so it's become more negative. So we look at fluorine, right? Okay, F minus, it's gained an electron, so we would have one electron on this left-hand side. Okay, so a way to remember this in terms of oxidation and reductions, loss of electron is oxidation, so the Leo says GR. Okay, so loss of electrons, oxidation, gain of electrons, reduction. Okay, Leo says GR. So that's one mnemonic you can utilize. The other one that people commonly like to use is oil rig. Oxidation is loss, is the oil. Reduction is gain. So whichever one of these works for you, I would suggest having it in the back of your head, just because sometimes it can get a little bit confusing. Reduction reactions, or reduction oxidation reactions, otherwise known as redox reactions, are electron transfer reactions. So what that means is something gains electrons, something loses electrons. And the half reactions that you see here, so basically just the oxidation or just the reduction portion of an equation, is how we're going to initially deal with these electron transfer reactions. So if we look here at this example, we have magnesium, okay, which is in its zero oxidation state, right? And it's going from the zero oxidation state, so a metal state, right, to its +2 charged oxidation state. So what has happened here is this this magnesium has gone from a zero oxidation state to a +2 oxidation state. So it has lost electrons. Notice the electrons here are being shown as being lost. Okay, the oxygen here that we have right there, it's one of the diatomics, and so it's in its natural state, so the oxidation state is 0. Notice over here we have an anion, we have the 2- anion. Okay, so the oxygen went from having a 0 oxidation state to a -2 oxidation state. It has become reduced, so we know that we've gained electrons. So reduction has occurred here. And what you guys should notice is that if we put these two together, okay, as you see here, notice that you have your reactants, okay, and then you have your subsequent new products. But you also have your electrons. What you need is to notice about the electrons is the number of electrons gained and lost have to be equal. So they're going to have to be able to cancel out. And we're going to look a little bit more at this very soon here. But for right now, what we need to understand is that we're going to be able to write oxidation and reduction half reactions. Okay, and notice that on the oxidation half reactions, we have something losing electrons and becoming more positive. And on the reduction half reactions, we have something gaining electrons and becoming more negative. We actually see this physically manifest when we read about examples. Okay, so right here we have a zinc bar, so zinc metal, Zn, as we'd write it here. Okay, this zinc metal is in a solution of copper sulfate. Okay, and we've looked at the activity series and we know how this works. We're all somewhat familiar with it, or at least we should be. So we know that these two are together in solution. And what ends up happening is because of the cell potentials, or excuse me, rather the potential for oxidation and reduction to occur, we actually have an exchange here. So what ends up happening is the electrons from the zinc ion get passed to the copper ions floating in solution and subsequently reduce the copper 2+ ions, and you end up with this nice, beautiful reddish copper setup that starts to form on the zinc bar. In the meanwhile, what you need to realize is that those zinc 2+ ions are now what starts to float in solution. Okay, and we have another example over here, something similar happening, okay, with our gold and copper. And once again, it follows the same trend. So there's actually going to be a physical response or physical manifestation of these transfers sometimes. So we're actually going to see color changes or physical growth on pieces of equipment that are submerged in solution.